Have you ever stopped to think about how engineers design something for a force they literally can't see? I mean, we're talking about things like wind, heat, stress, all these invisible elements that can completely make or break a new car or a plane. Well, the solution is kind of like digital magic. It's all about turning these forces into something engineers can actually see and shape. So let's break down how they make it happen.
Okay, let's take this car for example. You want it to be super fuel efficient, right? And stable at high speeds, and of course, quiet inside. All of that, every single bit, depends on how air flows over its body. But here's the thing, engineers face a really basic but huge challenge.
It's that simple. You can't see the wind. Sure, you can feel it, you can measure its effects, but you can't see it. You just can't look at a car and see that complex dance of air swirling all around it. And if you really want to optimize a design, you absolutely have to see exactly what you're working with.
And this is where modern engineering gets so cool. They've come up with these incredible tools that take mountains of complex physics data and just turn them into something an engineer can look at, explore, and really understand. They are literally making the invisible visible.
So, welcome to the digital wind tunnel. The technology behind all this magic is called computer-aided engineering, or CAE for short. And believe me, it is a total game changer. It lets engineers test their designs in a virtual world long before a single piece of metal ever gets bent.
At its heart, CAE is all about simulation. It's this powerful suite of software that runs mind-bendingly complex physics calculations to predict how a product is going to behave in the real world. Think of it like a crystal ball for engineers, but, one that's based on incredibly precise mathematics.
Let's get specific and look at one tool, NVIDIA's Kit CAE, to see how this actually works. At its core, it's a powerful visualizer. It takes the raw output from those physics simulations, which are just massive files full of numbers, and it transforms them into these interactive 3D models that an engineer can spin around, slice into, and really truly investigate.
So, how does it really work, step by step? Well, let's follow the process. It all kicks off with getting the basic data for the virtual car loaded into the system.
The workflow is actually pretty straightforward. First, you import the 3D shape of the car itself, the geometry. Then, you layer on the simulation data. This is all the information about airflow and pressure that a supercomputer has already calculated. And finally, you just got to make sure it's scaled correctly for the virtual stage.
And yeah, getting the scale right is a small step, but it's absolutely crucial. In this example, the data came in using meters, but the virtual stage uses centimeters. So the engineer just applies a simple 100x scale factor, and bam, everything is dimensionally accurate. Okay, so the model's in the system. Now for the really fun part, turning all of those numbers into actual visual insight. This is the moment engineers start seeing the physics come to life right before their eyes. One of the most direct ways to visualize all that data is to just paint it right onto the surface of the car. Here you can see different colors represent different physical properties, like the pressure the air is pushing on the car's body. The color bar shows us what's what, maybe red for high pressure and blue for low pressure.
And this is where the real analysis kicks in. Engineers can pick any scalar quantity. That's just a fancy term for a single value, like pressure or temperature. In this case, they're looking at something called wall shear stress, which is basically the friction of the air rubbing against the car's skin. Instantly, they can see exactly where that friction is highest, which is what creates drag.
Okay, so seeing the surface is great, but that's really only half the story, isn't it? The real action is happening in the air surrounding the vehicle. So how do you see that?
The answer is Streamlines, and this is probably one of the most powerful tools in an aerodynamicist's toolbox. The best way to think about it is like releasing thousands of tiny digital smoke trails all at once, where each one traces the perfect path an air particle would take as it flows past the car.
And just like that, the invisible becomes totally clear. You can see exactly where the air is flowing smoothly over the hood, where it breaks away from the roof, and where it tumbles into these turbulent messes behind the car. And that's where you get drag and instability. Streamlines show us the path of the air, for sure. But what if you need to know the pressure or the velocity inside a specific chunk of that airflow? You need a way to look inside that 3D volume of air, right? For that, engineers use what are called slice planes. Honestly, think of it like a medical CT scan, but for airflow. You can create this virtual 2D plane and then move it anywhere you want, right through the front, over the top, behind the car, and see a color-coded map of the conditions at that exact spot. It's amazing.
Now, for all this to work,
The system has to be pretty flexible, because it turns out the data that fuels all these visualizations can actually come in a couple of different basic formats.
So on one hand, you've got mesh-based data. This is where all the points are connected together into a surface, kind of like a digital sculpture with a skin. On the other hand, you have point-based data, which is more like a 3D cloud of individual, unconnected dots. They both have their uses, and a good tool like Kit CAE is designed to handle both of them.
But here's the crucial thing. It doesn't really matter how the data starts out. Whether it's a connected mesh or a cloud of points, the end goal is always the same. Turning that raw data into real, actionable engineering insight.
Okay, let's zoom out for a second. We've seen all these incredible visualization techniques, but what does it all really mean in the real world? Why does this whole virtual testing thing matter so much?
Well, the impact is just massive. Engineers can test dozens of different designs in the time it used to take to build just one physical prototype. This leads directly to more fuel-efficient cars, quieter cabins, and safer vehicles. It saves millions of dollars in development costs, and, maybe most importantly, it lets us get a much deeper understanding of the complex physics that engineers are trying to master.
And all of this leaves us with a pretty fascinating thought. For centuries, we designed things based on what we could see and what we could touch. But now we have the power to see the invisible forces all around us. So the real question is, what incredible things are we going to design next?